The James Webb Space Telescope, JWST, continues to excite scientists around the world because of the knowledge of the universe that it will unlock. However, we don't need to wait long to see what the Space Telescope is capable of, as its super-Earth discovery is already making astronomers rethink what they know about the universe. What are super-Earths and what has the JWST discovered about them? Has it finally found life on these planets? How do super-Earths affect you as a person? Join us as we dive into the James Webb Space Telescope's discovery about super-Earths that shocks the entire space industry. What do you expect from a telescope that costs $10 billion and took decades to build? Scientists are finding out just that with the James Webb Space Telescope that is now in its permanent orbit. The floodgates of information about outer space are about to open as scientists are waiting for their turns to study the universe using the power of the JWST. One of the key features of the JWST is that it has a cold side and a hot side. On the cold side is where observation is done, while the hot side contains solar panels and an antenna for two-way communication with Earth. But this arrangement only works if the Sun and Earth are always facing in the same direction from the spacecraft's point of view. There is a specific location in space where this condition can be met. That is where an object can orbit the Sun and always see the Sun and Earth in the same direction. This is the so-called L2 point, and this is where NASA parked the JWST. L2 is one of 5 locations in space called Lagrange points. They're actually named after Joseph-Louis Lagrange, who studied them in the 18th century. At these locations, the gravity of two massive bodies, which in this case are the Sun and Earth, combine to maintain a third, smaller body like an asteroid or spacecraft in a fixed position relative to the first two. However, the Lagrange points aren't stationary because they revolve around the Sun at exactly the same rate as the Earth, meaning the distance from the Earth always stays the same. In the case of L2, it is always about 1 million miles or 1.5 million kilometers away, around 4 times as far as the Moon. The Moon is less than a quarter of the distance away from the Earth. This positioning gives the JWST a much clearer view of the universe than what the Hubble gets in low Earth orbit. However, there is a massive disadvantage. Unlike the Hubble, JWST is basically too far away for repairs if necessary, so there will be no sending of astronauts to fix things that break. NASA hasn't even worked out a way to refuel the space telescope when the fuel runs out. Everything has to work perfectly on the first attempt, which is one of the reasons why it's taken NASA the best part of 2 decades to get the telescope ready for launch. The JWST's optical instruments see in infrared, and there is a good reason for that. This concept may be hard to grasp for humans because we always see in terms of visible light. However, when it comes to astronomical objects, they produce emissions across the whole of the electromagnetic spectrum, from very long wavelength radio waves to very short wavelength X-rays and gamma rays. Objects cooler than the Sun, like planets and new stars, tend to radiate at longer wavelengths. This is why NASA scientists settled for infrared when designing the JWST. Another reason is that while the dust in galaxies absorbs visible light, it's virtually transparent to infrared waves. This means even Sun-like stars can be easier to see in the infrared if there's a lot of intervening dust. Work on the JWST started over 30 years ago at STSCL, when the Institute's director Riccardo Giacconi challenged scientists to think about the next major mission beyond Hubble. The mission concept began to take shape in September 1989 during a workshop held at STSCL even before Hubble was launched. The workshop detailed the scientific opportunities and technological challenges of such a mission and built on earlier research up until that date. From a functional point of view, both JWST and Hubble are designed on the same principles. For example, both of them are built around a large primary mirror, which is what captures as much light as possible from objects that the telescope is observing. So basically, the bigger this mirror is, the better. In Hubble, the primary mirror is 8 feet or 2.4 meters in diameter and made from a single circular piece of glass. If this was scaled up to the size needed for the JWST, around 21.3 feet, 6.5 meters across, then not only would it be extremely difficult to fabricate, but the result would be too large and heavy to launch into space. So NASA ingeniously broke the mirror into 18 different hexagonal sections, which were folded up for launch and then deployed into an operational configuration once in space. The mirrors were made from beryllium and not glass, and coated with a thin film of pure gold. Thanks to this large mirror, the JWST can help us see where Hubble can't. Now, you can't talk about the JWST's components without mentioning the sun shield. It's necessary because the telescope is always exposed to bright sunlight in its orbit. This is actually great for the equipment in the spacecraft bus, but is not healthy for the optical instruments and science modules. This is because they see in infrared and must not be contaminated by heat from other sources. The function of the massive sun shield, the size of a tennis court, is to keep the hot side of the telescope at about 100 degrees Celsius and the cold side at minus 237 degrees Celsius. It is made from special materials and in 5 different layers. NASA sent the $10 billion telescope to space for 5 distinct reasons. The JWST was supposed to cost $500 million, but here we are. One objective of the JWST is to study the early universe. It is our chance to get as close to the Big Bang as possible. Scientists are excited to see the formation of the first galaxies about 13.6 billion years ago. The JWST will also see what these galaxies looked like before they matured. Now we see them as well-arranged or orderly, but they used to be messy. The JWST is telling us how messy they were. It will also spy on the formation of black holes, said to be present at the center of most galaxies. Apart from that, scientists are gearing up to better understand the life cycles of stars. Just like living organisms, stars are born, grow old, and die. Their remains may be used to form new stars. Lastly, which is the most important to us here, JWST will help in finding other worlds. In fact, let us just say one of the most exciting areas of contemporary astronomy is the search for exoplanets. Exoplanets are planets orbiting other stars. Scientists suspect there are Earth-like planets out there that may have the chemical ingredients and conditions necessary for life to evolve. The JWST will contribute to this search in several ways, using infrared imaging and spectroscopy to study the chemical and physical properties of planetary systems. Its ability to peer through the dust and snap super high-resolution images will give astronomers a direct view of planetary systems. For instance, we will know more about the newly formed star Beta Pictoris in its earliest stage. The JWST will look for the signatures of life by analyzing the chemical composition of exoplanet atmospheres. This again is something an infrared telescope is ideally suited for, because the molecules making up planetary atmospheres tend to be the most active at these wavelengths. Scientists so much look up to the JWST that Dr. Mike McElwain, JWST Observatory Project Scientist, said he expected JWST to become a household name, with folks discussing the latest images from the telescope at the dinner table. The time slots for using the JWST have already been decided and allotted. It is a general observatory, meaning that competitive proposals were selected from scientists worldwide, and they were used to develop the observing plans. The proposals were judged by a peer review system, using teams of independent scientists that ranked the observing proposals according to scientific merit. The process was completely anonymous to eliminate bias. The highest-ranked proposals were selected, and the results of these successful studies will be published in scientific journals, and the data will be made available through the internet to other scientists and the general public that want to study them further. In fact, this was how Hubble's time was allotted. Even if you were not a scientist, you can enjoy the stunning pictures taken by the JWST. The Hubble became popular as the public marveled over the amazing images it produced because NASA made them available to the public. In the same way, JWST images will travel around the world. One of the places in the universe where the JWST is likely to find evidence of life is the red dwarf star known as TRAPPIST-1. It is home to the largest group of roughly Earth-sized planets ever found in a single stellar system. The star is located about 40 light-years away, and the findings scientists have made about it are simply mind-blowing. The JWST will pick up the discovery with its higher capacity from where other telescopes stopped. TRAPPIST-1 planets have remarkably similar densities. That could mean they all contain about the same ratio of materials thought to compose most rocky planets, like iron, oxygen, magnesium, and silicon. But if this is the case, that ratio must be notably different than Earth's, because it means the TRAPPIST-1 planets are about 8% less dense than they would be if they had the same makeup as our home planet. 3 of the 7 planets in the TRAPPIST system were discovered using the Transiting Planets and Planetesimals Small Telescope, or TRAPPIST, hence the name of the system. They were then studied for over 1,000 hours by the Spitzer Space Telescope before it was decommissioned. All of the 7 planets are so close to the star that they orbit that they will fit into Mercury's orbit around the Sun. Because of this close distance, they were discovered using the transit method. Because scientists can't see the planets directly, they're too small and faint relative to the star, they watch out for dips in the star's brightness, which happens when the planets cross in front of it. The difference in density between the TRAPPIST-1 planets and Earth and Venus may seem small at about 8%. However, on a planetary scale, the difference is not insignificant, and it can lead to many interesting conclusions. For instance, one reason the TRAPPIST-1 planets are less dense could be that they have a similar composition to Earth, but a lower percentage of iron. Some scientists estimate the iron content to be about 21% compared to Earth's 32%. Another explanation is that the iron in the TRAPPIST-1 planets might have high levels of oxygen, forming iron oxide or rust, so the presence of the additional oxygen would decrease the planet's densities. In comparison, Mars's surface derives its red tint from iron oxide. However, similar to its three planetary neighbors, it has a core made up of non-oxidized iron. By contrast, if the lower density of the TRAPPIST-1 planets were caused entirely by oxidized iron, the planets would have to be rusty throughout and could not have solid iron cores. So can water cover the surface of each of the 7 planets? Water is even lighter than iron rust and would have changed the planet's overall density. However, given their densities, the 4 outer planets would have been made up of water compared to 0.1% for Earth. However, due to their being so close to the stars, for water to remain a liquid in most cases, the 3 inner TRAPPIST-1 planets would require hot, dense atmospheres like Venus, such that water could remain bound to the planet as steam. The TRAPPIST-1 system is fascinating because it allows scientists to learn about the diversity of rocky planets within a single system. The JWST will also be used to study the so-called super-Earth planets in more detail than ever. Super-Earths are fascinating for scientists to study because of the promises they hold. They have some of the highest chances of hosting life outside the Earth. Super-Earths are planets that have more mass than Earth, but are not as massive as the giant ice planets Uranus and Neptune. Uranus and Neptune are 14.5 and 17 times more massive than Earth. Generally, a super-Earth is about 2 times more massive than Earth to 10 times more massive than Earth. The fact is, there are no firm definitions for super-Earths, and different sources use different mass categories, but you get a general idea. NASA has discovered and catalogued more than 5,000 exoplanets. About 1,500 of them qualify as super-Earths. Of course, super-Earths are defined only by their masses, not by their composition or other characteristics. Scientists say there are lots of them, and we have barely scratched the surface. Some of the nearest stars to us apparently host super-Earths. Many of them have similar densities to Earth and are likely to have similar compositions. Scientists believe that the extra mass of the super-Earths could make them ideal for life. This is because of the stronger gravitational pull they possess. Take super-Earth Kepler-20b, for example. It's almost twice the size of Earth and 10 times more massive. This means its surface gravity is almost 3 times stronger than what we experience on Earth. Stronger gravity is actually great because it means the planet can hold on to more air molecules and form a thicker atmosphere. You want a thicker atmosphere because it offers greater protection from harmful space radiation. It also means mountains and hills will wash off faster, leaving a relatively flatter surface compared to Earth. Did you say who wants a flat, boring landscape? Actually, scientists claim this could actually birth dozens of shallow islands across the planet, and shallow islands are what are needed for life to form and evolve. Just as biodiversity in Earth's oceans is richest in shallow waters near coastlines, such an archipelago world might be enormously advantageous to life. However, there is one problem with Kepler-20b that will make a visitor think hard before firing up their spacecraft. Leaving this super-Earth is extremely difficult. Kepler-20b has more than double the escape velocity of Earth. This means rockets would need more fuel to reach their destination. For example, a mission similar to the Apollo moon landings would require twice the amount of fuel, meaning rockets could only carry a fraction of the payload. Or let's use SpaceX's Falcon Heavy rocket as another example. On Earth, the rocket can launch 50,000 kilograms of cargo or payload to orbit, but on Kepler-20b it can only manage about 40 kilograms, the weight of a German Shepherd. So while you're on Kepler-20b, you need to find a way to lose weight, or you are stuck on the super-Earth forever. Another fascinating super-Earth is the 55 Cancri E, also known as Janssen, discovered in 2004. In fact, it is interesting enough to be chosen as the JWST's first mission. It's located near 55 Cancri A star, one of 2 stars in a binary system about 40 light-years from Earth in the constellation Cancer. The existence of 55 Cancri E was suspected when astronomers noticed subtle tugs on the parent star. They initially thought 55 Cancri E had an orbital period of 2.8 days, but they realized later that the planet is much closer to its parent star. Observations with Canada's MOST space telescope showed the super-Earth has an orbital period of fewer than 18 hours. 55 Cancri E is not the most comfortable place to be because the temperature could reach as high as 2,700 degrees Celsius. Janssen has an atmosphere that is comparable to Earth's, only much hotter. Initially, the temperature data was taken as an indication that large deposits of lava existed on the surface. However, after reanalyzing this data and combining it with a new model previously developed, scientists began to doubt this explanation. According to the latest findings, Janssen must have a thick atmosphere, mainly because lava lakes exposed to space would create hotspots of high temperatures. Also, the temperature differences between the day and night side of Janssen may not be as significant as previously thought, which is another indication of an atmosphere. By comparing changes in the planet's brightness to energy flow models, scientists reached the conclusion that an atmosphere with volatile materials was the best explanation for the high temperatures. Temperatures on the day side could average 2,300 degrees Celsius, while on the cold side it could drop to minus 1,400 degrees Celsius. What is the composition of Janssen's atmosphere? It is likely similar to Earth's, that is, it contains nitrogen, water, and even oxygen. While much hotter, the atmospheric density also appeared to be similar to that of Earth, which suggests the planet is most likely rocky in composition. On the downside, the temperatures are far too hot for the surface to maintain liquid water, so scientists have to search elsewhere for signs of life. Scientists initially thought 55 Cancri E's interior was made up of carbon such as diamonds and graphite, but the conclusion was challenged by University of Arizona astronomy graduate student Johanna Teske. She maintained the parent star of 55 Cancri E is both cooler than the Sun and has more metals. She also said that the earlier study that reached the conclusion did not properly analyze the single oxygen line in the star's spectrum, leading to possible errors. Her own research found that the host star of 55 Cancri E has 25% more oxygen than carbon. However, there are many mysteries about 55 Cancri E that scientists have not been able to solve. For example, there is the question of how the super-Earth has not lost its atmosphere to space. This is because, given how close the planet orbits to its star and the fact that it's tidally locked, it would be subject to intense amounts of radiation. The second super-Earth that the JWST will study is LHS 3844b. It is located 48 light-years away from Earth in the constellation Indus and orbits a red dwarf star named LHS 3844. It was one of the first exoplanets discovered by the Transiting Exoplanet Survey Satellite, TESS. LHS 3844b orbits its host star at 0.06839 AU, so it is very close. In fact, it takes only around 11 hours to complete an orbit around it. Due to this extreme proximity to the star, it's unlikely to have retained any atmosphere, thanks to the amount of radiation it receives from its star. The planet has a radius of about 1.32 times that of Earth's and a mass of about 2.25 times that of Earth. While scientists will use the JWST to get more details about LHS 3844b, other telescopes have made discoveries about these exoplanets before it. For example, the researchers at the University of Bern show that the night side of the planet is tectonically active. LHS 3844b looks to be tidally locked, meaning one side of the planet is permanently facing the star. It's the same with the Moon looking at it from the Earth because we only see one side of it. The star-facing side, or day side, of the super-Earth reaches a temperature of about 770 degrees Celsius, while the night side is much colder. Temperatures there could dip below minus 250 degrees Celsius. So is there any effect of this high variation of surface temperature on LHS 3844b? The University of Bern researchers strongly believe so. They concluded that it possibly affects how material flows in the planet's interior. They reached this conclusion after running simulations with different strengths of material and internal heating sources, including from the planet's core and the decay of radioactive elements. Most of their simulations showed that there was only upwards flow on one side of the planet and downwards flow on the other. This implies that material flowed from one hemisphere to the other. What surprised them was that the direction of the flow was not always the same. But the flow has consequences. The upward flow of material on LHS 3844b can cause a large amount of volcanism on whichever side of the planet it flows. Most likely, the super-Earth has a hemisphere where volcanism is very common and another that has none. Similar flows on Earth are what is responsible for volcanic activities in Hawaii and Iceland. There are another two super-Earths that will make good candidates for scientists to study using the JWST. In fact, they're also among the most likely exoplanets to support life. They are GJ180d and GJ229ac. They orbit the red dwarf stars GJ229a and GJ180, which lie about 19 light-years and 39 light-years from Earth respectively. On the universe scale, these super-Earths are not so far away, and this is why they are very good for scientists to study. Red dwarfs are smaller and dimmer than the Sun, so their own habitable zones lie much closer in than they do in Sun-like systems. However, one thing about these habitable zones is that they often occur where planets tend to be tidally locked to their stars. But tidal locking is not really great for habitability because it means there is a scorching hot side on a planet and an extremely cold side. But then scientists say if the planet has a thick atmosphere, it can help with a more even temperature distribution. But then the two super-Earths here are far enough away from their stars to avoid tidal locking, making them quite special. In fact, GJ180d is the nearest temperature super-Earth to us that is not tidally locked. GJ180d's mass is at least 7.5 times that of Earth, while GJ229ac is at least 7.9 Earth masses. GJ180d completes one orbit every 106 Earth days, and GJ229ac does the same every 122 Earth days. Let's hear what you think of super-Earths in the comments section below. Can we find life on them?